Welcome back. In this lecture, we'll work with another data type in Python, the ndarray. We'll discuss its functionality, its importance in Python, and then we'll go over how to use it. For starters, these ndarrays originate from the NumPy package, so we most definitely need to import it before we get going. Now that this is out of the way, we should mention that ndarrays are a special data type in Python. They can store multiple numeric values in a sequence. And the best part is, unlike many other data types in Python, operations with arrays work element-wise. In other words, if we add up two arrays, the result will be a new array with the appropriate sums of the elements in each position. More on that in just a bit. As a side note, you may want to know that throughout the history of Python, there have been several packages which tried to create data types that work the same way. That is, element-wise. Some of them even have a very similar name, array-like. However, the Python community felt a need for a unified data type that can incorporate the fundamental functionality of each of its predecessors. Enter NumPy and its ndarray. This data type became the industry standard for computational operations in Python. So, let's get to it and declare one right now. To clear up any confusion, please don't forget that the letters nd relate to n dimensions. In mathematics, we use the letter n to designate natural numbers. Likewise, our arrays may have 1, 2, 3, or more dimensions. Therefore, whether we say an array or an ndarray, we practically mean the same thing. Okay, we start off by creating a variable. We'll call it array A and set it equal to the function nparray. Inside the parentheses and between square brackets, we write some numeric values separated by commas. The result of this code will be an ndarray that contains the numeric values. To verify that the code worked as intended, we can use the type function on array A. If you need a hint, this will output the data type of the variable we plug in. Unsurprisingly, we get NumPy ndarray as the output. To settle on the difference between an array and an ndarray, please remember that the creators have chosen array as a name of the NumPy function that will create an ndarray object. Since the latter means, in fact, a multidimensional array, we'll stick to convention and refer to an ndarray as an array for brief. Now that we have ensured that array A is of the desired type, let's go back to the previous cell and examine the output more closely. We see the word array, and in parentheses, the same values we entered earlier placed between squared brackets. This matches the description we made earlier, a sequence of numeric values. So once again, this array fits our expectations. Alternatively, we can also call the print function to display the values on the screen. The only difference is we don't see the word array as well as the parentheses. A convenient feature of ndarrays is their shape because it tells us how many elements they include. If we refer to the shape attribute of array A, we see the number 3 followed by a comma. We read this output in the following way. The shape of array A is 3, comma. In other words, we have a one-dimensional array of size 3. Speaking of, we can have arrays of higher dimensions too. For instance, let's define a 2D array. We'll call it array B, and just like array A, we set it equal to nparray. However, this time we'll use double square brackets and put the smaller individual arrays within single square brackets. If we take a closer look, it's like having an array of arrays, which is exactly why we call it a 2D array. To better represent the concept, imagine it in geometric terms. We can think of a 1D array as part of a line and a 2D array as part of a plane. In terms of data tables, you can think of a 1D array as representing values on a single row or column and a 2D array as a collection of rows and columns. However, even though this new variable looks different, it's still an ndarray. We can check that by calling the type function once again. The output just proves this to be the case. Next up, let's print out the 2D array. We see something that resembles a table consisting of 2 rows, where each row is an array. On top of that, each array has 3 values in it, so it's like a 2x3 table. Let's refer to the shape attribute once more. We can observe that this time the output contains the number 3 after the comma, not before, which was the case with array A a minute ago. This means that array B consists of 2 1D arrays, each containing exactly 3 elements. That's why as we refer to the shape attribute, we see 2 and 3 separated by a comma. If we think about 2D arrays as tables of data, this just means we have a data set of 2 rows and 3 columns. If we wish to get only the number of rows or only the number of columns, we can do this by indexing. By adding 0 between squared brackets, we get the number of rows. They constitute the first dimension of our 2D array. If we put 1 instead, we get the number of columns. They constitute our second dimension. Hence, we can get the size of each dimension of an array by indexing its shape attribute. Okay, we mentioned how 1D arrays resemble lines and 2D arrays resemble planes. So what will points resemble in this scenario? Well, those will be 0-dimensional arrays, or simply scalars. Let's define a new variable, array C, and set it equal to an NP array once again. This time, though, we only put 1 value inside the parentheses, without using any squared brackets. Then, we call the type function and see that it is an ND array too. However, if we display it, we only get a numeric value without any of the square brackets we had before. Why so? The reason is that what we have in array C is just a number rather than a conventional array full of multiple values, so it doesn't need brackets. Also, if we examine its shape, we see that it is void, which further proves the point. As a single value, array C possesses no length or shape in this case, which makes it a 0-dimensional object. Geometrically, we can think about array C as a single point in n-dimensional space, as opposed to a point located on a given line, plane, or hyperplane. Interestingly, though, we can have a single value that does have a shape. Let's define a new variable, array D. Set it equal to an NP array, and then put a number like 15 between squared brackets. If we check its type, it's once again an ND array. However, if we print it, we get the squared brackets we had for larger arrays. In addition, if we call its shape attribute, it states 1 followed by a comma. This is similar to what we had with array A at the beginning of the lesson. That is because we have an array that only happens to have 1 point. In this case, however, you can think of this point as being located on a line in the geometric space. Even though this might not look useful straight away, my coding experience has proved to me that certain functions and methods require inputs of a fixed number of dimensions. Hence, even if we need to pass a single value, it might have to be expressed as a small array or matrix. As an example of the latter, you can consider the same integer being stored as a 2D array in array E, right? As a quick reference to how many dimensions your array contains, you can just look at the code. Check the number of opening or closing brackets you have. If it is 1, then you are having a 1-dimensional array. If 2, then you are having a 2-dimensional array, and so on. This feature is crucial because it means ND arrays can contain single scalars, sequences of numbers, or even tables of values. They are computationally stable and universally accepted in the Python community. However, their syntax very closely resembles another data type, lists. In the next video, we'll discuss what sets arrays apart and why we rely on them so much. Thanks for watching.